Today, we're delving into the mind-bending realm of modern physics to unravel the secrets of one of the most revolutionary theories ever conceived in scientific history, the theory of special relativity. In the centuries following its inception, the Newtonian view of the world reigned supreme, captivating scientists with its explanatory power. Almost every phenomenon seemed to find its place within the Newtonian framework. However, as the 19th century drew to a close, an accumulation of perplexing experimental data emerged, defying explanation within the confines of Newtonian theory. It became clear that new theories were needed to address these anomalies. Three particular challenges stood out. First, light exhibited wave-like behavior, yet the mysterious medium through which it propagated, known as the ether, eluded detection and comprehension. Second, the equations governing electricity and magnetism clashed with Newton's understanding of space and time, creating inconsistencies that begged for resolution. Third, while Newtonian physics successfully explained the mechanisms of everyday activities on Earth because Earth was considered stationary, a lingering question arose. How could this framework hold up in the vast expanse of the universe? Could it account for the complexities of space, where celestial bodies, including Earth itself, were no longer stationary, but rather constantly in motion? Fast forward to the 1940s, where a new puzzle emerged in the form of muons, radioactive particles with varying lifetimes at different altitudes. This enigma sparked a renewed interest in incorporating the theory of relativity to explain the observed results. It served as a great example on how the theory of relativity triumphantly confirmed its relevance and applicability. But before we investigate the problem of muon decay, in order to fully understand the theory of special relativity, it is important to delve into the mind of the person who created it. It is important to understand how the theory itself came about and the thought process behind that triggered such an influential and groundbreaking theory. And the mind that we need to delve into is the mind of Albert Einstein. It was in 1896 that the brilliant Albert Einstein began his extraordinary journey into the depths of physics. Over the course of his life, he dedicated himself to unraveling the mysteries of the universe. While initially a part-time pursuit during his student years, Einstein's fascination with the fundamental workings of nature never wavered. The problem of light and motion became a constant companion, driving his relentless pursuit of knowledge. And it was at the tender age of 16 he imagined this. He stood before a plane mirror, contemplating a remarkable scenario. He envisioned himself being carried forward with the mirror at the speed of light. In this extraordinary thought experiment, he pondered a profound question. Would he be able to see his own reflection in the mirror under these circumstances? Einstein envisioned light rays emanating from different points on his face, traveling towards the mirror, bouncing back, and then reaching his eye. According to the prevailing theories of Galileo and Newton, these light rays would have zero velocity relative to Einstein if he moved forward at the same speed as light. However, Einstein's revolutionary insights began to challenge this established wisdom. Einstein reasoned that if light waves followed Maxwell's equations, a cornerstone of electromagnetism, then a transformative shift in perspective was necessary. By imagining a frame of reference moving at the speed of light, he argued that light waves would appear stationary and non-advancing. This led to the creation of the two postulates of special relativity. Number one, the laws of physics are universally valid in all frames of reference. And number two, the speed of light, denoted as c, is an absolute constant, independent of the motion of the source or observer. To appreciate the significance of these postulates, let's take a step back to the days of Sir Isaac Newton. Newton formulated his laws of motion based on the assumption that Earth was stationary, serving as a fixed reference point against which all other motion was measured. However, despite the undeniable usefulness of Newton's laws, in explaining a myriad of Earth-related activities, Einstein's revolutionary proposition upended this long-held belief. Einstein proposed a radical departure from the notion of Earth's absolute rest. Instead, we can extrapolate that the speed of light, a constant and unalterable entity, should be considered stationary, serving as a universal frame of reference. Everything else, including motion and especially time and length, would be relative to light. So just like Newton stopped Earth, Einstein stopped light, but not literally, of course. Furthermore, special relativity reveals a fascinating consequence. Nothing can surpass the speed of light. This realization positions light itself as the perfect benchmark for objects in motion to be relative to. Now, let's dive into a fascinating problem that helped confirm the validity of the theory of special relativity. Enter the muon, a subatomic particle generated in particle collisions. When cosmic ray protons from the Sun collide with atoms in the upper atmosphere, they create pions, which rapidly decay into muons and muon neutrinos. These muons travel at speeds close to the speed of light, maintaining their direction. However, muons have a short lifespan of around 2.2 microseconds and quickly decay into an electron and 2 neutrinos. Here's where the mystery begins. Despite their short lifespan, muons rain down on Earth's surface at high speeds, and during their descent to the ground, a considerable number of muons should decay due to the limited lifespan. In 1962, physicists David Frisch and James Smith from the MIT conducted an experiment to shed light on this intriguing phenomenon. Setting up the experiment atop Mount Washington, they measured the number of muons present in the atmosphere. At an altitude of 1,910 meters or 1.9 kilometers, their counter detected 563 muons per hour. They then descended to sea level and repeated the count, expecting a significant decrease in muons due to their short lifespan. According to non-relativistic calculations based on Newtonian physics, speed equals distance over time, only 27 muons per hour should have been detected at sea level, as most of them would have decayed during the 6.4 microsecond journey. However, to their astonishment, Frisch and Smith observed 409 muons per hour at sea level, which unsurprisingly matched the predictions of the theory of special relativity. This experiment demonstrated the effects of high-speed travel, where time slows down and lengths contract, according to the principles of special relativity. That's it for today's Concept Crunch video on special relativity. We hope you enjoyed this journey through the formative views of Einstein's remarkable theory. Stay tuned for our upcoming videos where we'll dive deeper into the mind-bending concepts that emerged from special relativity, such as time dilation and length contraction, and its impact on our understanding of the universe. Remember, keep questioning, keep exploring, and keep fueling your thirst for knowledge.